All right, this is a video on extra examples from 3.2, extrema and the first derivative test. We're talking about relative extrema. These are, remember, places where you have a difference in increasing function to decreasing function or decreasing to increasing. If you go from increasing to decreasing on your function, you have what's called a relative or local maximum. If you go from decreasing to increasing, you have what's called a relative or local minimum. So we want to make sure we know how to find them. So remember we have you take the derivative, you set that equal to 0 and find your critical values. And those critical values we then test to see what's happening on each side to figure out if it's a relative max or min. The first derivative test said, let f be a continuous function with a critical number c. So remember that's something that made the derivative equal 0. If f prime changes from negative to positive at x equals c, then it's a relative minimum. If it changes from positive to negative at x equals c, then it's a relative maximum. If it's positive on both sides or negative on both sides, then it is neither a relative min nor a relative max. So that's, remember, something that we'll talk about in the next section, which is a point of inflection. So right now it's just neither, since we haven't discussed that. So for example 2, we want to find all the relative extrema for the following function. So to be able to do this, we need to take the derivative of what we're given. So f prime of x, that would be 2 times negative 3, so that's negative 6x to the first, plus 1 times 2, so that would just be 2, and then x to the 0 would be gone away, and then nothing for the 7. We set that equal to 0 to find our critical values. And I would just add over the 6x and then divide by 6. So it looks like x equals 1/3 is our critical number. Now what we want to know is that actually a relative min or max? So what we do is we place it on a sign chart, put the number right there in the middle. We talk about the intervals on each side. This is negative infinity up to 1/3, and this is 1/3 to positive infinity. We pick a test value in each region. Something less than 1/3, I can use 0. Something bigger than 1/3, I could use positive 2. And then we plug it into the function, the first derivative. So this is negative 6 times 0 plus 2. That's an overall positive sign. And then negative 6 times 2 plus 2, that's going to be an overall negative, because that's negative 12 plus 2. So if you have a positive in that region for the first derivative, that means you're increasing. If you have a negative in a region, that means you are decreasing. And if we go from increasing by the first derivative test to decreasing at a point, that means that this is a relative max. Okay, so this is not just 1/3, it's going to be a point. So we need to figure out what's the other part of 1/3. So 1/3 something is a relative maximum. To find out what that something is, we plug it back into the original function. So anytime you're looking for an ordered pair, you need to plug back into regular f of x. And we're going to work this out. So 1/3 squared would be 1/9, so that's negative 3 times 1/9. This would be 2/3, and I'm going to make this 7/1. Negative 3 and 9 reduce, that's negative 1/3 plus 2/3. Go ahead and get a common denominator for this last one, times it by 3/3. That would make that minus 21/3. So this is going to be positive 1, and then take away that, that's going to be negative 20/3. So that is my actual ordered pair for my relative maximum. Okay, let's look at number 4. Number 4 is another polynomial, so we need to take the derivative of it. So let's get our ink. So this is f prime of x equals 4x cubed minus 32. We can factor out a 4 here once we set this equal to 0. That would make that x cubed minus 8. That is perfect cubes, so we have to remember how to factor that. So when you're dealing with perfect cubes, you need to make sure you know how to factor it. It's a binomial times a trinomial. So this would be x for the cubed root of x cubed. Cubed root of 8 is 2. So then in the trinomial part, you multiply these things in pairs. So x times itself is x squared, x times 2 is 2x, 2 times 2 is 4, and then the signs are always the same pattern, same as the original, opposite to the original, always positive. So then when we set these equal to 0, x equals 2 is definitely going to be a critical value. 4 doesn't give us anything because there's not an x. But when you set this one equal to 0, that's supposed to be a plus, it doesn't factor. So if we do quadratic formula, x equals negative b plus or minus square root b squared minus 4. Let me write that better. I'll show them all my work. B squared is 2 squared minus 4ac all over 2a. This part right here is the most important. That's 4 minus 16. That's going to be negative. If it's negative, that means this doesn't count for us because it's imaginary. We're only looking at real numbers. So we only have to do the 2. So I'm going to make my chart. This is negative infinity to 2. This is 2 to infinity. This would be a 0 for a test value, maybe positive 4. Plug them into the derivative. That would be 4 times 0 cubed minus 32. That's going to be negative. This would be 4 times 4 cubed minus 32. That's 64 minus 32, so that's going to be positive. So on this part we are decreasing, on this part we are increasing, which means we're going downhill and then back up, so that makes this a minimum. And that happens at 2, so we need to get the other part of that ordered pair. So f of 2 is 2 to the 4th minus 32 times 2 plus 4. That would be 16 minus 64 plus 4. So that's going to be negative my brain just stopped for a second, sorry. This is going to be negative 44 altogether. There we go. So then this would be the ordered pair. 2 comma negative 44 is a relative min. Okay. When I highlighted this before, we had the another day in class, so we actually chose to do 6 in class, and so 5 is getting put on the video. Now for this one, the derivative of this, we have to do the chain rule because you have something inside the parentheses. So you bring the 3 to the front. So this is 2 times 3, parentheses x minus 4. This loses a power, so now it's squared, but then we times it by the derivative of the inside, which is just 1. So f prime of x is 6, parentheses x minus 4 squared. If we set this equal to 0, it's already factored. You can imagine writing x minus 4 twice. You're just going to get x equals 4. So that's our only actual critical value. So when we plug that into our table, this would be 0 and maybe 5. So this is the interval negative infinity to 4 and 4 to positive infinity. Plug those into our derivative. And our derivative is 6, parentheses, x minus 4 squared. So this is 6 times 0 minus 4 squared. That's 6 times 16, because negatives are going to turn into positives, so this is going to come out positive. 6 times 5 minus 4 squared is 6 times 1 squared, so this is also going to come out positive. So that means this is neither a relative max or min, because you had 2 pluses back to back. So it's just a continually increasing function. Okay, so let's look at our next one. We did define absolute extrema. Remember, those are on a closed interval. What is the absolute highest and absolute lowest that the graph gets on that closed interval? And the reason this is different sometimes than relative max and min is because a relative max or min does not have to be the highest the graph ever is. It just has to be a turning point between increasing and decreasing. Whereas an absolute means that's the highest or lowest that you actually get. So f is continuous on a closed interval AB, then it will have both a minimum value and a maximum value on that closed interval. Now we did some of these in class, so let's find the ones that we had skipped. All right, so one of the ones we did not do was number 3. Find the absolute extrema on f of x equals 4 minus 6x over x squared plus 9 on the interval 0 to infinity. You could try getting a common denominator here, but because there's plus or minus between these, you can actually take the derivative of both parts. The derivative of 4 is 0, and then for this part, I'm going to have to do some scratch work. We're going to have to do the quotient rule. But we do have that minus sign in between them. So the reason we have to do the quotient rule is because this has a top and bottom that both have an x. So I'm going to do some scratch work to get this derivative. So I'm going to let my top part be 6x. So the top derivative or top prime would just be 6. The bottom is x squared plus 9. So the bottom's derivative would be just 2x. Okay, so remember for the quotient rule, we still have this minus in front. The 0 doesn't really count. But we do, remember the derivative of the top, so that's 6 times the bottom minus the top function times the derivative of the bottom all over the bottom squared. So this would be, I'm going to keep my negative out front for right now. This is 6x squared plus 54 minus 12x squared all over x squared plus 9 squared. And then we're going to let the tops combine like terms. So I have negative and then negative 6x squared plus 54 all over x squared plus 9 squared. I can then distribute my negative on the top, and that will actually help me make this a little bit nicer because that'll make this positive 6x squared minus 54 over x squared plus 9 squared. Okay, so there's my derivative. When you're dealing with derivatives that have both x's and top and bottom, and you're talking about critical numbers, your critical numbers have to come from anything that makes the top 0 or makes the bottom undefined, as long as it's not undefined in the original function, because then that's not going to cause anything to happen. So the bottom is never 0 on the bottom, because you're going to square something and then add 9 to it and then square it again, so you're always going to be positive. So we get no critical values from the bottom. But from the top, we can set 6x squared minus 54 equal to 0 and solve that. So I'll pull out a 6, and this ends up factoring to x plus 3 and x minus 3, and then I get negative 3 and positive 3. So those are my numbers that I got from solving the top. Now the most important part is we have to look at our interval that they told us to be on. We're on 0 to positive infinity. So negative 3 is out because it's not in that interval. So it was kind of not even something that we can use because it's not in the interval we're looking at. So when you're doing these absolute extrema, you don't actually do the same sign chart we did before. You just make a column for each thing. So the endpoint is always first. So this is 0, so that's an endpoint. Then any critical values that come between u and the end, so that would be 3. And then because this goes on to infinity, there's just going on forever. So we don't really know what's going on out there because it's going to infinity. So we're going to plug in these, remember, into our function. We're testing them into the function. What y value do they have? So not into the derivative. So f of 0 plugged into this would be 4 minus 6 times 0 over 0 squared plus 9. That's just going to be 4. And the f of 3 would be, so we'll have to probably do some work for that one, 4 minus 6 times 3 over 3 squared plus 9. That's 4 minus 18 over 9 plus 9. So this is 4 minus 1, which is 3. I could use my calculator to do that, but that's also going to have a value of 3. So in this interval, this is actually the absolute max, and this one is the min. And remember, that's ordered pairs. So 0, 4 is the absolute max, and 3, 3 is the absolute min. Now, the reason I can grab these numbers, the test value or endpoint numbers with this, is because we plugged it into the original function already. Okay, so let's look at the next one. This says find the absolute extrema on f of x equals 12 over x plus 2 on the interval 0 to infinity. So we need to look at this one. First of all, the original function has a discontinuity. At x equals -2, because that makes the original function divide by 0. The last one did not have that because it was, again, always positive on the bottom, because you had the, I'll just go back up for a second, you had the x squared plus 9 in the original bottom, and that's never 0. So anytime your original function has a 0 in its denominator, you do have what's called a discontinuity. So if we do the derivative of this, so the top function is 12, so top prime is 0. The bottom function, and I don't have to do it by quotient rule, but I'm doing it this way, is x plus 2, and the bottom derivative would just be 1. So then remember, this would be derivative of the top times the bottom minus the top function times the derivative of the bottom all over the bottom squared. So that's -12 over x plus 2 squared, which, remember, I could have found by writing 12 x plus 2 to the -1 and doing the power rule there. So another way of finding that same derivative. Just depends on which way comes to you easier. Okay, and so we're looking at this right here, and notice that what we think the critical number is what makes the bottom equal 0, because the top is just a number. It can never equal 0. You would think it's x equals -2, but a discontinuity cannot be a critical number. So if you have something in your original function that makes you divide by 0, it can't be a critical number. So then the only thing we need to test is just the endpoints of this interval right here, which 0 is the only one because it's actually going on to infinity. So if we test 0, because this is going on to positive infinity, we do our original function, apply 0, so that's 12 over 0 plus 2, which is 12 divided by 2, or 6. So this would be a max, and we have no min, because there's nothing smaller to compare this to. So the min does not exist. Okay. And the reason that we know that this is a maximum instead of a minimum is because I didn't state this a second ago, is because this function right here, the f prime, your f prime of x is always negative. Because you have this -12 on top divided by something that's always going to be positive. So if your f prime of x is always negative, it's always decreasing. So as we move farther to the right, the y values are going to get smaller. They'll never actually get to a smallest point because it's actually just going small forever towards infinity, but that's why the minimum doesn't exist. But the max is then the starting point of this graph. So that is the end of section 3.2 video.